under the search, type in academic challenge. We have all six of the videos of the 6 winners of the academic challenge. So not only did you see the Columbia University one, but you'll see all the other ones that were winners of our challenge. So it's all on the website, and it's there now.
All right. My name is Larry Bartosik, and this talk is about delivering power to the space elevator climber. The problem is megawatts, okay? 20-ton climbers take a lot of power, especially at the bottom. And there are several zones that the climber climbs through. It has to accelerate from 0, it has to get up to a certain power level, and it has to then move at constant velocity, around 200 kilometers per hour for many, many thousands, tens of thousands of kilometers. And then it has to decelerate as it gets to geo. Now, you can imagine powering up the climber to start the motors and start the magnetic fields that produce the torque at the bottom with some kind of extension cord at the bottom, but it can't go very far. And there are reasons for that are the tether, even though it's a good conductor, is not that much better than copper. And over relatively short lengths, you begin to lose a lot of power to I squared R. But here's the real question. When you're designing a power system for the space elevator, how much do you actually need? And the bare minimum of power is you have to put 53 megajoules in every single kilogram just to move it from the surface of the Earth out to geosynchronous orbit. So if you're looking at a 20-ton climber, which is 20,000 kilograms, you need a terajoule of energy to get there. And that's not including the kinetic energy of being in geosynchronous orbit, because the tether provides that for free, stealing it from the rotational power of the Earth, okay? If the trip takes 8 days, then the average amount of power that you're using over the length of the trip is 1.5 megawatts. But the problem is, it's not evenly distributed like that. If you look at the force of gravity, it drops off as 1 over r squared, okay? And this black dotted line here is 36,000 kilometers up at geosynchronous orbit, and you notice there's a 0 there. The effective gravity at that point is 0, and as you go past that, you start to get a few percent in the opposite direction, things trying to throw you away from the Earth. But you can see there is a lot of power required if you try to get to the 200 kilometers per hour very close to the surface of the Earth. You would need as much as 11 megawatts of power in a 20-ton climber. We have talked for many years about putting a 4 megawatt limit. We have to look at that very carefully. And the reason people thought a 4 megawatt limit was reasonable was because you see you don't need that much power down below. Once you hit 5,000 kilometers, you're under 4 megawatts, and it keeps dropping, and it drops very quickly. The problem is that's completely devoid of what motors need, okay? And so first let's talk about what did Edwards propose in his book 20 years ago. In the space elevator, he proposed a ComPower free electron laser, keep those words in mind, working with custom-designed gallium arsenide photovoltaic cells, 59% conversion efficiency. That's very high. We have not hit 59% conversion efficiency. 540 kilowatts per square meter of power density. That's another number to keep in mind, because I'll show you some numbers later. So the PV arrays, the photovoltaic arrays on the construction climbers would start small at 4 meters in diameter. That's problematic for a different reason that I'll show you in a moment. And they would go up to 10 meters in diameter, proportional to climber mass. A transmitting laser that he was talking about would be 12 meters in diameter. It would be a giant telescope like the Keck telescope with adaptive optics to point the beam at the climber's receiving array. So this concept is the conceptual design from the 2023 study, which involves 10 motors, 10 wheels, 5 wheel pairs squeezed together on the tether. And I just show for scale how much is a 10 meter diameter array compared to the climber, how much is a 5 meter diameter array. And you can see that the 10 meter diameter array is pretty large. Now, I'm assuming, I'm trying to solve this problem in the simplest way possible by starting at the surface of the Earth. So at the surface of the Earth, we have wind, okay? We also have gravity. The array has to be able to survive wind and gravity. And it has to survive that gravity way up through the atmosphere, because just above the atmosphere, gravity is practically as strong as it is on the Earth. Wind is only a problem up to 20 kilometers. Above that, air becomes so undense that it doesn't provide a significant force. The motors that I started with in this design, this motor is a Magni 650 motor, which was designed by a company that was trying to make electric aircraft. I originally designed the climber to use that motor exactly and discovered it didn't have enough torque. Once I had designed the climber, it needed 10 wheel pairs. It couldn't lift itself, let alone any payload. At this point, I had to say, okay, we don't have a motor on the market that can deliver the torque required. And I extrapolated the Magni 650 by a factor of 2, which I thought was reasonable. We could get twice the torque out of a motor that weighed the same as the Magni. So that's where the numbers come from for the power requirements. These things operate at 800 volts, just like a Tesla car, and 10 motors per climber would give you 11.2 megawatts total electrical power at full torque and rated speed. So there's a three-prong approach to designing the laser beaming system. First, you have to look at what does the atmosphere allow? Then you say, once I know the wavelength that the atmosphere allows, what laser technology satisfies that wavelength? And then you have to look at what do I receive that wavelength with? How do I convert the light back into electricity? There are two windows in the atmosphere. The first window is the visible window, and you can see, and the orange phantom line is at 0.5 microns, which is a green visible laser line. If you were to move more blue, if you were to go to a shorter wavelength, you would begin to get into Rayleigh scattering, and there would be more absorption losses in the atmosphere. You can also get out of the atmosphere at around 10 microns in infrared, and I'll show you what the problem was with going with infrared. Every laser diverges as it propagates away from its source. And this divergence is controlled or governed by this equation. And what you can see about this equation is the larger the wavelength is, the faster the beam diverges. And the smaller the waist, the W0, is, also the faster the beam diverges. So I did a number of cases. I looked at the 0.5 microns green laser, and I calculated how much does that beam diverge from the surface of the Earth up to geosynchronous orbit. And then I said, I'm going to match, so I start with a 2-meter diameter laser, and I'm going to put a 2-meter diameter PV array. Well, when this laser gets up to geosynchronous orbit, it is almost 12 meters in diameter. So I came up with a ratio of the area of the fixed PV array to the variable size of the laser light to determine how much the power is lost. And for a 2-meter diameter laser transmitter, you lose 95% of the power. And if you look at these power numbers in the power curve, they fall off faster than the climber needs, okay? So then I said, okay, well, let's bump it up to a 5-meter diameter laser. The power drops by 45%, but everywhere on that power curve is above the power required in that previous graph. If you look at 0.5 microns and 10 meters, you only lose 5% of the power. But I don't need to not lose any power because the power goes down very fast, okay? So, and I also want to make things as small as reasonable. And I'm going fast because I have a lot of material here. What happens when you change the wavelength? 0.84 microns is right in the middle of the range for gallium arsenide photovoltaics. It's near infrared. By making the wavelength just a little bit larger, you lose 70.3% of the power. So the conclusion about diffraction is, make the beam waist as large as reasonable, put wavelength in the 5 micron range, and a smaller diameter laser is cheaper and more feasible. So try to build the system with a transmitter in the less than or equal to 5 meter diameter range. Now here's the other thing, the advantage of the loss is that the light that misses the climber can be collected at geosynchronous orbit by photovoltaic arrays because you are still shining light up there almost 100 times greater in intensity than sunlight, which means the PV arrays in geosynchronous orbit can be smaller than solar arrays. So it's another way to save money. So then you have to ask about atmospheric transmittance. The atmosphere is going to eat up some power. How do we put a number on how much power the atmosphere absorbs? It's only 0.3% of the total travel of the power beam. All the rest is in vacuum, which is completely governed by the diffraction equations that I was just talking about. This is a very convenient curve here. It shows the amount of power received as a function of wavelength outside the atmosphere and at ground level. And if you look at the numbers, 950 watts per square meter above the atmosphere, 650 watts per square meter at the surface of the Earth, no clouds, the atmosphere is basically eating 31.6% of the laser power. Now this is based on sunlight, but I drew a line at exactly 0.5 microns, 500 nanometers, and used those numbers as if all the light was in that wavelength. Okay, we know what wavelength we're going to transmit now. What laser does that? If you can't put a laser, if you can't make a laser that's 6 megawatts or 11 megawatts, you need a bunch of little lasers to do that. People have tried to do coherent beam combining of small lasers, and it's a very difficult problem, and it's difficult to get right. It's better if you can do it in one big laser. Adaptive optics, we know how to do that. One of the issues is how do you turn the power down as the climber doesn't need as much power without losing the beam quality. If you lose the beam quality, you lose more power at the receiver than you would have just from a high quality beam. And then does it need to be tunable over a range of frequencies? So there's possible green laser choices. Argon ion lasers, real low power. Copper vapor lasers, they emit nanosecond pulses. Erbium doped upconversion lasers. Again, these are all small, it'd be very difficult. Dye lasers can be operated in the green spectral region with tunability. Green laser diodes, very difficult to manufacture, low power. Here's a great idea. The free electron laser, just like Brad was talking about 20 years ago. You take an electron accelerator, you run a batch of electrons through an undulator, and you wiggle the electrons so that they produce light in the frequency you're interested in. 20 years ago, I put a proposal in with Jefferson Lab. They were being paid by the Navy to design a free electron laser for, obviously, defensive purposes. I didn't win the proposal. I wish I had, because I'd be that much ahead of the game. But they figured out it was possible to make a free electron laser much more compact than you might guess, and they could fit it on a 747. And they were talking about a free electron laser in the megawatt range. In this part up front here, that's where you'd expand the beam up to, because you're not going to have a beam tube with the electrons going in it that's 5 meters in diameter. You need some optics to expand the laser light that comes out to the 5 meters that you want. Now, what do you receive it with? The first type of photovoltaics, and the most common, is polycrystalline silicon and single crystal silicon. And you notice again, there's that phantom line in orange at 500 nanometers, which is down at the low end of what silicon is good at converting. Multi-junction solar cells, which are intended to convert a wide range of frequencies from the sun. If you look at the indium, gallium, phosphorus subcell, has a terrific response to 500 nanometer light. You don't need the other ones. You don't need the other junctions. You'd have custom photovoltaics that are all indium gallium phosphorus. So what are the characteristics then? Each half climber carries its own array. And we assume that at startup you can exceed the 4 megawatts. And it looks like from the design that I'm proposing here, you would only need 290 kilowatts per square meter, which is not quite half of what Brad was proposing. But the efficiency Brad was assuming was way higher than we've been able to get. So here's the optimization problem. The 0.5 micron light is a little short for efficient conversion, but it's the best wavelength range to get out of the atmosphere. So you put together a custom semiconductor mixture that allows you to convert, and you might be able to get as high as 40% efficiency. Here's what I refer to as the money shot, the transfer function. What I've done is I've put all the layers of efficiency together into a single equation that shows that, and some of these efficiencies are a function of altitude. For example, if you are near the surface of the Earth, you don't have to worry about the atmospheric transmittance because you haven't gone through enough atmosphere to absorb, so that efficiency looks like 1. So that's why I say when I calculate the efficiency of the system at the surface of the Earth, it looks like the system efficiency is about 15%. So if you need 11 megawatts, you need to put 73 megawatts of wall power into the lasers to make it work. If you are reasonable in limiting the system power to 4 megawatts, then only 27 megawatts of power needs to go into the system. Naval nuclear reactors are in the perfect range to do that. At GEO, the system efficiency has dropped down to about 5.7%, but the total amount of power required is very small. Well, I mean, it's nothing when you get to GEO. So the reason I included this picture is because in the 2010 Space Elevator Competition, the teams that were bringing their toy climbers to climb up brought their own light sources. And one of the things that people noticed after the fact was the light sources were reflecting off the PV arrays and coming back down as infrared, and they were strong enough that if people had walked into that range, their hair might have caught on fire. And they were just lucky that no one did that. So we have to think about that. The other thing you have to think about, the 0.5 micron light is very hazardous to eyes. So everyone who works in this facility would be wearing goggles all the time. Even the reflected light would be hazardous. The last thing I did just before this conference was look at how do I send power up to a 100-ton, or a 200-ton climber rather. I started with 10 20-ton climbers and coupled them all together. And the first thing I noticed was when I tried to shine light on each one of the PV arrays from each one of those 20-ton climbers, they shadowed each other. So I had to come up with a pattern of pairs of laser arrays that would be able to intercept each one of the climbers without causing shadowing. Well, that meant something that I've never had a chance to design before, a mechanism that allows the PV arrays to point at their laser transmitters. And you basically need 2 degrees of freedom. You need a yaw rotation of the PVs around the bottom of the climber, and you also need a pitch orientation to get them to point correctly. Now this shows only 5, and I stopped at 5 because when you put all 10, the picture changes scale and it gets much harder to see. But what you would see in a full array is there would be 10 pairs of lasers. Now we're talking about launches once a day, which puts 7 climbers on the tether at any one time. That would mean you'd need only 7 of these pairs of laser transmitters. But because of the torsional stiffness of the tether, they may rotate around. And if they do that, you probably want to complete the circle and have 10 laser transmitters. You can also do other things with the other laser transmitters, like, for example, mitigate debris heading towards the tether. Those lasers may be tuned in such a way that they ablate the materials that are in low Earth orbit and cause them to deorbit. I'm done. That's it.
Well done.
Oh, he can take some.
I can't believe I got that in.
Larry, you can take a little bit of my time, because I'm on.
Okay, then one question out of your time. Okay, one question. One question.
If I remember correctly, you said at Geo the kilowatt per square meter was about 80 times the radiation from the sun.
Yeah.
What's the heating effect, and what kind of heat management would be needed, if any,
That is
climber?
actually, I think I make that point in here that the biggest problem is keeping the PVs cool enough. And heat management on the climbers is an enormous problem that is currently being worked on, because low-level heat, low-temperature heat that you're trying to dispose of in space is a big problem. That's what made that circular blue shell all the way around. That's supposed to be a thermal shield, a thermal radiator for getting rid of the low-level heat. I'm thinking what we actually need is a refrigeration system that allows us to raise the temperature of the evaporator so that the motors, the lubricants in the bearings, and the liquid coolant around the motor never get over 200 C. But the space radiator can be smaller in area because it's hotter. I just haven't had a chance to work all that out.
Okay, we've got time. Paul, you're up. Thank you. We now have a better design. Yeah, that's you.